Thank you very much, Leisha. I'm just going to start myself. Okay, thank you all for coming. Similar to Maeve, I'm going to tell you the story of how I've ended up doing my research. Primarily, I'll talk a little bit about other aspects, but primarily about research. And I'm also going to talk about the journey that I took to get there. So first, a bit of a mission statement. I am passionate about energy. I am passionate about renewable energy, and I think that we should be aiming to eliminate fossil fuel use in Ireland. This is a picture that you're going to see again later. This is a part real, part fake picture. This is Mount Lucas Wind Farm in County Offaly. It's a Bord na Móna wind farm, and this facility in the foreground is a planned hydrogen plant, which I'm going to be talking about a lot in my presentation later on. But first, so I think like most engineers in this room, I spent a lot of time building Lego, so I could have showed a picture of some of the cool Lego stuff that I built. But what I'm going to show instead is a collaboration between two future different types of engineers. So my brother over here, who studied electronic and computer engineering, myself. This is one of our many projects that we spent most of our childhood making. You can see that obviously I'm using my mechanical engineering skills to hammer in the bentest nails you've ever seen, because the timber, the timber that we had available was too thick. And these are training wheels, and there's Fergal making the steering system. So we spent weeks and weeks making this car. I can't remember why we painted it white. I think it was maybe the only paint we had available. But once we got it made, it weighed an absolute ton. And unfortunately, when we took it to drive, then we'd sort of forgotten the fact that our parents' driveway was gravel, so it never actually drove anywhere. But it was the journey was really enjoyable. So I think based on this kind of childhood, and some of the people here would also know that my father is a mechanical engineer as well, and I think I was always sort of destined to end up in this building, Nuns Island, where I learned my trade as a mechanical engineer. I had fantastic lecturers there. I was really blessed and had a fantastic time. But I just maybe want to touch on three lecturers who have had an impact on what I'm going to be talking about tonight. And this is absolutely not to exclude any of the other esteemed lecturers of mine who might ask me a really difficult question later on. But Prof Rory was one of my lecturers when I was here, and he used to get a lot of industry speakers into class, and he wasn't just bringing industry speakers in, he would bring people from non-profits in, and it was through his classes and his industry speakers that I really started to get a proper understanding of what climate change was, and then of the role that engineers could play in addressing climate change. It had always seemed like this was the 90s or the early 2000s, so it sort of felt like it was a bit far away and a little bit scientific and a bit esoteric, but having the speakers in that class really helped me understand what it was and how engineers could work on it. Nathan Quinlan, who I'm delighted is one of my colleagues now, but he was a brand new lecturer when I was a student, and he really talked a lot. He really showed me a lot about how to bring together the different fields of engineering and to be an engineer. So, I'd always felt that we had the mathematics, we had the engineering sciences, we had computer programming, and it was Nathan used to run a lot of projects that sort of made me see for the first time that these all fit together. You can use mathematics to solve engineering problems, and you can use computer programming to help you do that. So I thought that was really unique. And then Professor Ger Hurley here, so it's interesting Ger's getting mentioned in both presentations. So Ger lectured us mechanicals a couple of times, and the one that really stands out for me that sort of goes with this story is in power systems, which was, I believe, an optional class when we were in fourth year. He asked us to write a term paper, and he gave us three headings to write about: wind energy, solar energy, or something called hydrogen fuel cells. And I'd never heard of these things before. So I opted for this one, and I was sort of hooked on the idea. It sounded really, really interesting. So sort of armed with the purpose, the thinking of how to be an engineer, and this sort of expanding world of hydrogen, I started looking for postgraduate opportunities. I was really interested in learning more about hydrogen. But Why on earth would one study this? It's got a terrible name. This is the Hindenburg. And I only really noticed when I was putting this slide together, it looks like there's people standing at the top of that, which is remarkable. But so why on earth would one be interested in studying something like this? Well, you know, this is a slide that I show my students when I'm trying to get them to understand what governs the energy decisions that are made. First things first, Europe has got a lot of goals around energy. So the first one is that we need, as a continent, a 55% cut in our emissions by 2030. This is called the Fit for 55 package. After Russia invaded Ukraine, we started to see this new set of rules called Repower EU, and the whole idea was to get Europe off imported gas. We were hugely dependent on Russian gas, and it was being used essentially as a weapon against us. And then there's this long-term strategy to move Europe from being a highly polluting continent to a net zero carbon emissions continent by 2050. So this is the sort of the context I'm in, and again, why I do what I do. And specifically then bringing it to energy and the role of hydrogen, the European Union has got some priorities. It's got priorities around energy efficiency, around circularity, which is all about using waste as an input to some other product, around renewable electrification, and Maeve touched on that, and I'm going to touch on that a little bit more. And then for some areas, it's talking about hydrogen, and it uses this term hard to abate, okay? And that's a sort of a term that I'll sort of try and define in the next couple of slides. But it basically means that the EU and the member states of the EU are trying to move away from an energy system that looks like this, where we use oil for transport, coal and gas for heating, electricity generated in big centralized power stations, to a more sort of circular energy system where we have small-scale generation on people's roofs, we have wind farms, we might have some low-carbon power generation, we have lots of batteries, lots of other forms of energy storage. Everything is decentralized, everything is based on the resources that we have available to us, which for us in Ireland is renewables primarily. So these enablers, these paths that we have to go down. So societal behavior is going to make a huge role, is going to have a huge role to play in getting us off fossil fuels. Energy efficiency is going to have a huge role to get us off them as well. Electrification is going to have an enormous role of heating and of transportation. We need to start using, or we need to continue and increase the amount of renewables that we use in Ireland to meet all of these new electricity demands. While it might seem that it's very difficult for us to electrify, generating zero carbon electricity has been shown to be easier so far than decarbonizing other types of energy that we use. So we're going to need more renewable electricity, we're going to need more electrification. We're going to need to start looking offshore. This is what researchers call the real map of Ireland. Here's Ireland, and then our ocean area is 7 times bigger, right? So if we can crack offshore energy technology, we can really we can start to make enormous strides in becoming self-sufficient in energy and potentially being an exporter of energy as well. But, and this is bringing it back to why I'm interested in hydrogen, what's left, okay? There's some things that are going to be extremely difficult, if not impossible, to electrify. So these are things that vehicles that might drive very, very high mileage, trucks, coaches, maybe trains in some cases. Things that require very, very high temperatures, okay? Industry, this is Ireland's biggest energy use site. This is the Aughinish Alumina site in County Limerick. They require energy at 1,500 degrees Celsius. Achieving that electrically is extremely difficult. So they're stuck with burning things for some time to come. The chemicals industry, which is a big polluter, it relies on the chemical nature of oil and gas, okay? So if we are to imagine a whole society where we don't have fossil fuels, what's going to be the zero carbon source of the chemicals to make the plastics, the polymers, the composites that we're going to need for our society? And then there's really difficult things to think about. If those weren't hard enough, there's ships that sail halfway around the world. How do we fuel those? Aircraft that fly thousands of kilometers with hundreds of people on board. How can we decarbonize this? These are very, very These are seen as the hardest of hard to abate. This is where fossil fuels in many ways seem kind of magical because they are so energy dense. They're in a very, very small volume, you can fit a huge amount of energy. So how do we get those off fossil fuels? In addition to that, here's something that we see in Ireland. Here's an additional problem that we face in Ireland. And that's the problem of, while we do have a lot of renewable energy available to us, it's variable. It's only there when the sun shines or the wind blows. And mostly it's when the wind blows because the sun doesn't shine too much. So this is just a recent month of data. This is showing electrical energy demand in Ireland. And you can see it's fairly predictable. You can see the 5 weekdays. You can see the weekends in there. And this is the wind energy output. And basically, for want of a, just to simplify things way down, the gap between the red line and the black line is what needs to be made up by some other energy source other than wind. Okay? So if we have wind and if we have fossil fuels, then fossil fuels is filling that gap. So the gap at this time is quite small. The gap here is quite big. So one option, an option that I'm going to be mentioning a lot, is energy storage, right? So if we grab wind energy from times when we have too much, now in this particular period, we don't have any time where we have more wind energy than what we need, but this does happen, and it's happening more and more. Could we store that and use it to fill this gap? Well, just to give a sense of where we currently are with our energy storage, we have a big, what's called a pumped hydro plant in County Wicklow, and that involves, when we have excess energy, pumping water up a hill, and when we need energy, we let it flow down through a turbine. We generate electricity that way. The area here represents, to scale, the amount of energy that's stored. So you can see, to ride through this period of about 2 weeks of low wind demand, we would need an enormous amount of mountains that have been hollowed out to add these reservoirs. So then we think about batteries. That's our other big energy storage technology. Well, this is a 200 megawatt hour lithium-ion battery plant in County Offaly. It was, for a time, the largest battery plant in Europe, so Ireland is leading in this area. This, to scale, is the size of the energy storage problem. So again, we'd have to think of how many battery plants are we going to need to fill this gap between the low production and the high demand. So this is just to sort of motivate. So I'm not saying that there's going to be any one solution to it, but I'm going to talk to you about one potential solution that could address some of the challenges that we're facing now. So, armed with my interest in hydrogen, I applied to and was accepted into MIT, and I was thinking, this is fantastic. It's a really prestigious place. It looks great. I'm going to be hanging around in this dome and sort of just being, in the academic world. MIT also looks like this. And this is the building where I worked. That was the window. My desk didn't have a window, but that was the closest window to my desk. But for someone interested in energy, I was in a building attached to a power station, which was quite nice. It made it hot sometimes because these are the condensers. These were constantly throwing off heat. And as well as this power station, it made the electricity for the MIT campus. It made the heat, and it also, but it also, because it's hot in the summer, it provides air conditioning. So this plant is constantly running. So even on the hottest days, even in our office, we had an office between us. We could feel the heat coming off these condensers. Another, interesting feature was this kind of semi-abandoned train track, which seemed to run through the middle of campus. But twice a year, the circus would come to town, and the circus train would pull up. It was like Indiana Jones. Circus train would pull up on a siding directly across the road from me, and they would literally walk the elephants down the street, past MIT campus, and off to the Boston Gardens, where the big basketball arena where the circus would be. So it was a great place to be, and it was a great place to sort of focus the mind on all things energy, and that's what I did. My master's by research was on the area of hydrogen. I got my wish. I got to study hydrogen. Wasn't quite the topic I was thinking it was going to be. It was mobile phone towers. This was the early 2000s, there was a huge expansion going on in the mobile phone coverage. And one of the American mobile phone companies, I don't think they exist anymore, Nextel, they wanted to be able to put towers like this in places like this and provide them with energy. So, but in some of the places, they were trying to get the last 5 or 10% of people in America to have coverage from mobile phones. And but a lot of these places were too far away from the power grid. So it would be too expensive to build the power grid up to them. And as well, in these really remote locations, the power grid could be very weak. It could be very, very, very low voltage. It could go down at a moment's notice. So they all had, whether they were connected to the grid or not, they all had this little propane tank as a backup, propane being a fossil fuel, and they had these little engines that I couldn't believe the mobile phone infrastructure was reliant on little engines like this. And so this was, I spent a good few of my weekends driving around with a maintenance engineer called Larry in his huge pickup truck. This is at the top of a mountain in New Hampshire. And we visited dozens of sites like this, and they all had this little engine that ran off propane, and every couple of weeks a truck would go up and deliver propane to these. And they had backup batteries as well if the propane ran out for a few hours. So what my work was about was trying to build a decision tool for Nextel about under what conditions would different energy sources work. Could we run a site like this from renewables in a given site? Could it be solar? Could it be wind? What would we use as energy storage? And then how would our choices be influenced by how far from the grid we are? What the cost of diesel is. There's my US dollars per gallon, and then my metric kilometers. America's a weird place like that. So I sort of came up with these maps, and it was kind of crude, but we could start to see under what conditions different technologies would make sense for Nextel to use. So I really, really enjoyed that project. My PhD then was on the area of hydrogen, but moving from the renewable side to the fossil side, okay? Because hydrogen is what's called an energy carrier. And I'm going to describe how we could make it in Ireland later on, but essentially you need to put energy in to make hydrogen. You need lots and lots of energy, and that energy can either be renewable or it can be fossil. So I was funded by a big bad oil company to study the making of hydrogen from coal, but with the caveat that we were interested in integrating a process of capturing the CO2 from this process as well. And this is a gigantic coal-fueled factory complex in Tennessee that I got to visit a few times. This was where Kodak film was invented. Kodak film was all the chemicals in Kodak film all came from coal mined in Kentucky. And they operated a process called gasification. So that was what I studied for my PhD. And I was at a talk a few weeks ago, and someone said, I spent 6 months making this one graph. And this was my 6-month graph. It took me 6 months to make this graph, more or less. And it was a sort of a simulation tool, a multi-physics simulation tool that tried to inform operators of these gasification plants how they perform dynamically, how you could minimize thermal stresses in these systems, how you could maximize efficiency, how you could avoid the ashy, slaggy stuff sticking to the inside of this. So we had it was a really fun project, just getting completely lost in the details of making these really complex devices work better. And this was in one of my visits to Kentucky. This is the same plant at night, and I was woken up by this roaring noise, this huge, huge noise. And it was this, I looked out the window, it's difficult to see the scale, but I'm about 1 kilometer away from this. This huge flame was shooting up into the sky. And I could feel the heat through my window in my motel room from 1 kilometer away. So I took a few pictures of it and showed our hosts the next day, and they said, "Oh no, you weren't supposed to see that. That was an illegal venting of flammable gases at night that they had done." And it was because the gasifier had gone outside its operating conditions, had hit some sort of thermal limit, and they needed to get all the gases out, and they ignite them so they don't release flammable gases. So that was another really cool, is getting really into the nuts and bolts of chemistry, of some aspects of material science. And so by the time I finished my PhD, I was really interested in doing more technical things on hydrogen. So I returned to Galway. I returned to Galway, and what I'm showing in this graph is a graph that shows US government investment into hydrogen research, okay? Here's the period in the blue of when I did my master's and my PhD on hydrogen. I was in the sort of the golden era of hydrogen research in America, and I was thinking, this is fantastic, and I'll just take this off elsewhere. I met my wife, Sinead, while I was a student in MIT. So, you know, for family reasons, wanted to come back home. So I got a postdoc in Ireland with Henry Curran over in chemistry. But while I was a postdoc, the floor fell out of the hydrogen sector. It went through, hydrogen has gone through these hype cycles in the past. And interest was lost. It was seen as, no, this isn't the big deal that everyone made out it was going to be. The funding disappeared, and by the time I was trying to establish myself, and I was interested to hear Maeve's experience of trying to get yourself established as an independent researcher, there was no funding for the thing that I wanted to do most. But you couldn't, you know, you can't let that get you down. You have to try and innovate. You have to try and find your way around things. So I teamed up with some, you know, and this is just a small list of some of the people that were really helpful to me in getting me started as an independent researcher. Marcus and I worked together on some building energy simulations, did some work on Stirling engines, worked with Professor Sean Lean on biomass combustion and corrosion, again, getting into this materials side of things that I thought I knew about, and it turns out I didn't. Wastewater treatment with some of our colleagues in civil engineering and microbiology, and then with Jamie Goggins, we looked at some biofuels, and this sort of term, supply chains, is going to come up more and more. So I started trying to, and that's maybe something to sort of, if there's earlier stage colleagues here, that maybe something to keep in mind. You might not be able to get the funding for the one thing that you love. So you might need to think laterally a bit. What can you do to keep yourself going? And then I was keeping myself going, and then, you know, fate has this sort of weird way of intervening. And I got a cold call from this guy. This man's name is Paul McCormick. And he is an Armagh man, and Armagh men are not made to be trifled with. And he had just been hired as the head of research at an institution, a third level institution in Northern Ireland that by all rights had no business having anything to do with research except for Paul. It was called an institute called Belfast Metropolitan College, a college of further education. And he basically said, I want to lead the biggest hydrogen project in Europe. And I read your master's thesis. I don't know how he got it. Don't ask Armagh men how they get things. He read my thesis and he said, I want you to be on the project. And this was 2016. You know, just to go back a slide, this was when there was no funding. Certainly, this is just US stats, but the European figures are more or less the same. He wanted to get moving on this project. So that was the cold call. So I was thinking, this is great. I'm going to get in on this hydrogen project, and I'm going to get to do the really technical, detailed stuff that I had fallen in love with during my PhD, understanding all the multi-physics pieces of how hydrogen gets made. And he was interested in renewable hydrogen. So this was going back to the idea of wind and solar and things like that to make hydrogen. But then I missed a call. I don't know how I missed a call, but I missed a call from the consortium that was being established. And someone else, a French collaborator, jumped in and said, I'll do the really detailed multi-physics modeling of hydrogen production. And by the time I got back on, I possibly missed about 3 calls. Because by the time I got back, I had been given a job that to me didn't sound interesting in the slightest and sounded like, oh no, you know, do I really want to be involved in this project now? So I was tasked with working on supply chain models for hydrogen. And I was thinking, what on earth are supply chain models? So now I still wanted to be involved in the project, partly because I was afraid of Paul, but partly because it was just, there was a really good consortium of companies, of things coming, and I felt like the hydrogen sort of ship had, not airship, but the hydrogen ship had arrived. So I hired an excellent PhD student, Arya, and we set to work. And I'm going to describe a little bit what this idea of supply chains is. It's not as non-engineering as you might think it is on the outset. It's essentially just, it's a big mathematical model. And once we started thinking of it as a big mathematical model applied on a regional scale, as opposed to in a reactor on a micro scale, it got a lot easier for a mechanical engineer to be comfortable with that project. So what Arya ended up doing, among many, many things, among many papers that he wrote, was to map out all of the wind farms in Northwest Europe, map out how much energy was being wasted at those wind farms, so how much energy was not being connected to the grid because there was too much wind on the grid at that time, and then establish how much hydrogen could be produced if we were to turn that wasted electricity into hydrogen, and how much would it cost to get that hydrogen to the nearest big city to run their bus fleet. So how much hydrogen, how much would it cost, and how far would it have to be transported. So we did this, made this big mathematical model for the 40 biggest cities in Northwest Europe. And it was a fantastic project to be a part of. And that project it was an Interreg project, and Maeve talked about Interreg. Interreg is really interesting. It's a funding source that people don't talk about much, but it's primarily involved with building things, with doing things, with getting infrastructure built, with getting initiatives done. There is a research angle to it as well. So this is part of the infrastructure that was built. This is the first hydrogen production site on the island of Ireland, built in County Antrim, that was built as part of the GenCom project. So we got to do the modelling for this project, and this site is now operating, and it's now providing hydrogen for buses in Belfast. And that was based on this man's sort of just go ahead and get things done, but also on the supply chain modelling work that Arya led here in Galway. So what is supply chain modelling? So it's an equation, but it's not an equation. So it's basically at the root of what we do in supply chain modelling, to describe it, we're interested in minimizing something. So let's just say we're interested in minimizing the cost to a consumer of buying hydrogen. Well, this cost is going to be a function of how much it costs to make hydrogen, how much it costs to store it, because we can't just make it and give it to someone, because if it's being powered by renewable electricity, it's going to be producing at whenever the wind is blowing. But people, the consumer, they don't really care about when the wind is blowing or not. They just want hydrogen when they need it. So we're going to have to store it, and then we have to get it to someone. And then we divide that by the total amount of hydrogen, and we get this minimum price. And there's different technical terms to talk about it, but that's essentially the simplest version of what we do. Making it a little bit more complicated, underneath production, there's the cost of building the equipment to make, the cost of powering it, the cost of operating and maintaining it. And we do that with the hydrogen storage as well, and we do that with the transportation system to get the hydrogen from the production site to the end use site. And we can see then that we can start to, sorry, apologies about the quality of that, we can start to fit our mathematical models to this now. So this is just very, very simplified models of how we can relate the efficiency of our hydrogen production process with our mass of production, with the number of hours of operation. So we can start to fit what looks, again, like, you're sort of thinking to yourself, well, it looks like a fairly straightforward algebraic expression here. But the devil really is in the details of this. And that's because of the nature of the variability of renewables. These are, I'm not defining all my terms in the equation here, which is obviously bad practice, but the number of hours that this hydrogen production plant would operate, that depends really strongly on whether you have renewable electricity available to make the hydrogen or not. The amount of storage capacity, the amount of hydrogen that you need to store, that depends on what's the gap between wind being available to make hydrogen and when the wind next blows again. So all of these variables are dependent on the balance between the production and the consumption. So it's sort of, once we started applying an engineering rigor to this, we could see that there is actually something here. Oh, sorry, that's a repeat slide. So we started asking ourselves, well, has anyone done this before? What people have done this before? Because it kind of felt like it was a bit of a no-brainer to study, in a mathematical sense, how these supply chains work. And this is This is a more recent update of some literature review work that we've done. But we basically identified specifically in the area of storage, how has the state of the art handled the temporal nature of hydrogen production, hydrogen demand, and then the use of storage to balance the two off each other. We found that some did and some didn't. But then we started thinking about, well, picking one storage method. Hydrogen's a really, really difficult gas to work with, so there's lots of different storage technologies that people are interested in. Have these other people compared the different hydrogen storage technologies with each other? And the vast majority hadn't. A couple did. And then this idea of a parameter study. Nothing is certain when you talk about renewables. You might have a perfectly good wind profile one year and terrible the next year. So most modeling studies that do handle temporal production modeling consider a year. All right, but what we found was that no one had done parameter studies. No one had looked at what the effect of uncertainty on a hydrogen supply chain was. So we sort of worked out that, well, we do have a niche here. There is something we can go for. So that led to the concept then of our hydrogen supply chain modeling software. Now at the moment, well, I say software, it's not anything grand. It's a bunch of really smart PhD students sitting around, but sitting around and working hard, obviously. But we established then, here's our electricity source. Within our model then is the hydrogen production, the hydrogen storage by different means, the distribution by different means, and we can then set up the how that gets delivered to someone else. And the logic of it is over here, and I'm not going to spend too much time getting into the logic of that. But essentially, what we end up with is an iterative approach to calculate something called LCOH, levelized cost of hydrogen, and that's this determining factor that most researchers would use to establish, is hydrogen production and delivery and storage feasible. So we set to work, and once we had developed this technique, we started getting invited to lots and lots of projects, joining European consortia, designed projects, and provided advice. So this is one we're currently working on in Mallorca. This is our Belfast project. So we launched this thing called the Enabling Support Tool to help bus fleet operators decide what the optimum mix between battery electrification and hydrogen electrification for their buses is. We did some really interesting work with Valentia Island. They're interested in pursuing big-scale renewables, and they wanted to see what a potential role for hydrogen might be for them. But in the meantime, the teaching continued. So we were doing all this great research work, but I was teaching as well. And one of the aspects of the teaching that I do is for my fourth year and fifth year advanced energy systems engineering students, we go on a visit to Galway Wind Park, which is until very recently was Ireland's largest wind farm, just west of Galway here near Uachtarard. And this is the manager of the wind farm, John O'Sullivan. And this is a photograph of the day the idea of a research project was born. So on this field trip, John and I got talking, and I didn't really know John before this, but he started talking about curtailment. And curtailment is this problem that wind farms can have of if they're all producing too much electricity that the grid doesn't need, it happens at night a lot, then they're simply told, they're sent an instruction from EirGrid, and they're told, stop letting your blades turn. And all the blades are automatically turned from Dublin in such a way that they don't let wind push them around. And if you think about it, you're letting free energy flow over turbines. You're not letting the turbines turn. So we started talking about curtailment, and I started saying, well, have you considered batteries? Have you considered some way of storing this? He said, no, batteries are too small. And I mentioned hydrogen to him. We did a few scribbles on a piece of paper and recognized that, wow, there's a huge potential to produce hydrogen there. But it was just an idea. A few years later, Conor O'Dowd from Galway Port contacted the university, contacted the Ryan Institute, and I believe spoke with Jamie Goggins as well, probably, and was put on to me, and because he had this idea of hydrogen. Is hydrogen something we should be getting into? So that was an interesting little nugget. And then in 2020 as well, CIE came and they'd seen some of the hydrogen work we were doing and saying, well, not every bus route is suitable for electrification. Can you help advise us on hydrogen? So with these little bits and pieces of conversations, and I guess maybe another thing I'd just advise people, have these weird conversations with people because you never know what might come of them. We had someone who might be interested in producing hydrogen. We had someone who might be interested in using hydrogen, CIE, and we had someone who might be a landlord for a potential site. So this is suddenly becoming not a research idea in paper, which is mostly what my team deals with. It could be something that could happen in real life. So that started to grow legs at that point. Air Aran Islands heard about the idea and said, well, we'd like to trial hydrogen on planes that fly from Connemara to the Aran Islands, Aran Island ferries, and the company that maintains all the roads in the west of Ireland and uses a huge amount of fossil fuel energy said, well, we've got these really stringent decarbonisation targets. How can we address them? Can we talk to you? So we decided then in 2022 that we had to do something about this. You know, it wasn't going to be enough to just, here's a scenario case study for you, here's this case study for you. I sort of felt that we wanted to do something. So we put a consortium together. We applied to an EU funding agency called the Clean Hydrogen Partnership. Again, it's one of these funding calls that is not explicitly geared towards research, it's geared towards infrastructure. But research is a hugely important part, especially of an immature area like hydrogen. So in order to get that funding, we had to massively expand what our plans were. This could not just be a plan for Galway anymore. It had to be something more nationwide, something approaching a regional hydrogen project. Unfortunately, the person who initially spawned the idea in my head, John O'Sullivan's company, they had to leave the project, but we did get some excellent replacement partners in. And we arrived at a place at the start of this year where the project officially started. We had €8 million, most of it from Clean Hydrogen Partnership, €500,000 from the UK government. And we've got 5 years to build and operate this plant. And the project is led by University of Galway. It was initially being led by the wind farm operator of Galway Wind Park, but they had to leave, and basically to save the project, the university stepped in and said, we'll lead this project now. So what the concept of it is producing hydrogen from this not yet built, but has been granted planning permission, hydrogen site at Mount Lucas Wind Farm, truck it to Galway. The port has given us a site to construct our hydrogen hub. There's the railway. Kant Station is just up here. You might notice that there's lots of times there's wind turbine blades stored here when you look out the window. So this is being given over to us once we're ready to start building. This is the yard for the CityLink buses. This is the yard for CIE's Galway bus fleet and the coaches that go from Galway. And then this is the construction materials company where they use this, where they have to use lots of energy to keep bitumen flowing, because bitumen wants to solidify, but they need to pump it into trucks so they can get it out to the roads. So there's a little hub here of people that are going to find it very hard to decarbonize any other way. So that's what we're aiming to do, and to build a fueling station at Galway that will be used for decarbonizing buses, trains, trucks. This is this is what we told the EU we would do, so now we have to do it. But why is a researcher leading this project? Well, first things first is the companies involved, they weren't quite sure how they were going to make hydrogen, so I'll talk about that in a second. They didn't quite know how the demand for hydrogen might change over time, and they wanted to know what a supply chain might look like as it starts to grow and grow, hopefully. So we used our modeling expertise. I'm conscious of time here, I'm speaking really slowly. But this is our opportunity for interaction, because I've been doing all the talking. So when you're faced with a hydrogen project that uses renewables, you really don't know what the best way to make hydrogen is. People talk about this free excess wind power. This is this nighttime electricity that I was talking about in my slide. And this was what first got us interested in this project. Was it's free, right? It's going to waste otherwise, so surely that can make cheap hydrogen. Or could we use power that's coming from the wind turbines itself? It means having to buy electricity, but could there be a bigger demand? But what I want you to just do very, very quickly is which of these three options for making hydrogen would be the cheapest, Okay, and since it's an election year, we can get into the swing of it. So from free excess wind power, from wind power above a certain threshold from our wind farm in County Offaly, or from wind power with backup coming from the grid. So who thinks it's the first one? Raise your hand. Who thinks it's the first option? You use free electricity, and you have to vote, by the way, because I'm a professor. So, okay. All right, so there's okay, small number of people. Okay, from wind power above a certain threshold at the wind farm. So this means you have to actually pay for your electricity. Okay, okay. And then from wind power, and I forget the answer to this, the wind power that's backed up from the power grid. So you're buying electricity from the farm, and you're also buying electricity from the grid. Okay, a slight winner there. So here's what our modeling tells us. So the first one, unfortunately, people who chose the free excess wind power, you're the most wrong, because the problem with free excess wind power is that it is not available all the time. It's only available in fits and starts. Okay, and this is the first kind of thing that we had to confront. This confronted us in our research was, yeah, it's free, but who on earth would be interested in buying hydrogen that I produce every couple of hours? That means I need a huge tank. Well, maybe they're specific, but in the big picture, no. And I'd be fairly convinced of that. So, if you would need an enormous storage tank to hold that. This one works a little bit better, right? We've now got a more steady supply of electricity. It's not free, but it's more steady. On this one, we have production in the green here from the wind farm, and then the grid is backing us up. So we could theoretically run this one all day, all night, 24/7. So when we calculate our costs, production costs for the three, they all seem kind of similar. Okay, if you add these two together, it's production, the capital expenditure and the operational expenditure are all pretty much the same. But the storage cost sinks this idea. You need so much storage in order to ride out these periods where there's no hydrogen and your supplier is saying, where's my hydrogen? And then the idea of transporting it, because again, for huge chunks of the summertime, whatever transport system you're using to bring the hydrogen around is just sitting there doing nothing. Okay, so there's a huge amount of expense that's not used efficiently when you design a system like this. Systems like this are a bit more efficient because we've got more constant operation. So this was one of the big learnings that we were able to give to the industry partners when they're starting to conceptualize what they're going to do at their wind farm. So we can also do in our research group further studies. We can examine what the carbon intensity of these different types of projects is. And going back, you're saying, okay, wind power topped up by the grid is the winner. But then when we start thinking of the carbon footprint, the grid is not zero carbon electricity. So we get a major problem here. So does that mean this one is? Well, there's other approaches we can use. And this is, I'm conscious of time, so I won't have time to get into all the detail of this. But what I want to just show is that this is one aspect of how we can use research to help inform the rollout of these big projects. I'm going to skip on to, God, how did I think I was going to get through this? Typical academic behavior. But I just want to talk about what our current research directions are now, just to give a flavor, because that's what was. And this is now what we're doing now. We're now moving towards not just a kind of a deterministic approach to modeling hydrogen supply chains. We're trying to see, can we develop techniques that optimize hydrogen supply chains? So this is some work that we have developed for biomass in Sweden. We've been working with steel mills and paper mills in Sweden. Paper mills have got this toxic sludge that they need to get rid of. Steel mills use coal to make the heat to make steel. Can we use clever upgrading technology to transform the sludge into a fuel that could displace the coal? Because these are two huge industries in Sweden. So we were part of a European project where our Dutch partners were developing the technology and we were trying to inform the supply chain design. So we come up with, or my PhD student, who will defend in January, came up with this optimization tool where we can have a model that can run through and say, for different numbers of places where we do this upgrading of the sludge to this coal-like material, how can we pick the best location and the best size and then the best number of these places to do it? So that's just sort of a flavor for what we're doing on optimization. And I see this as being a really important advancement on what we're doing, because no one else is doing anything remotely like that. We're moving towards open sourcing. We've got a real mishmash of codes that we run, of models that we run. Some things in Excel, some in MATLAB, some in Python. We're moving towards doing everything in an open source fashion on Python right now. So we're on the cusp of hiring some postdocs, and we've got some really smart master's students in the Energy Systems program helping us out on that as well. And then this is another one, multi-criteria decision making. So this is the last slide I'm going to show. Don't worry, Leisha. But this is trying to decide, okay, so based on all the different factors that could influence hydrogen production, what are they? How do we weight them against each other? And can we represent that in a way that will inform where investment should go? So this is our kind of this was our alpha version of this. We unveiled this at the National Hydrogen Conference in Cork 2 weeks ago. And we're trying to see how different factors that influence hydrogen production. Okay, so these are different factors that we believe will influence hydrogen production. And we have developed a method of trying to weight these against each other. We do the same for where the end users and the potential end users of hydrogen could be, where the storage and distribution sites could be, and where the export sites could be. And I won't get into the details of why some of them look the same, but happy to outside. And we come up with this overall map, and we're attempting to find out, well, where would be the best places? This is early days yet, so we're still trying to feel our way around this, but that's really where our work is going at the minute. So the final thing is just this picture, which is one that I've sort of showed a few times that I like to see. This is one of the Apollo rockets as it's leaving the Earth's atmosphere. The first stage has just been released. The first stage is powered by kerosene, fossil fuel. The second stage is powered by hydrogen, which is more energy dense. You can see, I like to look at the difference in exhaust that's here. The polluting kerosene flame, the clear hydrogen flame. Okay, it's not the solution to everything, but it's an interesting technology that's worth studying. So, thanks. Thank you.